Okay, so we're going to have a look at a introductory level about the wave particle duality of light, first of all, and then electrons. Um, Before we begin, we need to have an understanding of diffraction patterns. So let's think of some water waves, and these lines here are representing the crests or tops, the peaks of some water waves. So there's a peak, and obviously in between here we're going to think about a trough, peak, and so on. So these lines here are representing the peaks. Now, when these waves hit a barrier that has a small gap in between it, they will diffract. So they will spread out like this. So these now are representing the peaks of the waves. If we have a barrier with two slits in it, a double slit, which is what we're going to be mainly thinking about to start with, is double slit experiments. So here's my barrier, and it's got two slits in it. Then we're going to have diffraction out of both of these slits like this. And then that's going to set up the possibility of some interference patterns. Sorry about that. Some interference patterns between the waves. Now this is really difficult to draw, so I'm actually going to go to an example here, and we'll talk about what's happening. So we've got our waves coming out here. Don't worry, I've actually cut off the bit where they're already being diffracted out of a single slit here, but we're coming out of our double slits here. And if we just have a look at this point here, we can see here that we've got the peaks of two waves interacting with each other at this point. And then we can see that that line is sort of carrying along here, and the same here. If we have a look in between these two here, then what we've got is a peak interacting with a trough, which is a little bit harder to see. So a peak interacting with a trough. So if we have a think first of all about what's happening where the peaks are interacting with each other, well, this is where we're getting wave addition, so constructive wave interference. So our waves are arriving in phase with each other. So the peaks are in line with each other. That's why on here we've got this crossover region here. And what that means is the waves are going to add, and we're going to double the wave height. So that's constructive wave interference. And I'll give you a link to some other videos where you can actually see the effect of this. Now, at these points where we're getting a wave here, so this wave is interacting with the middle of a trough, then we're getting waves arriving out of phase with each other. So the peak or the crest here is interacting with the trough. So we can see that there's only a peak of that wave there, and then it must be interacting with the trough, which is halfway through that wave there. And those waves are going to cancel out. So we get destructive wave interference. So constructive wave interference is where the peaks are arriving in phase with each other. Destructive wave interference is where they are arriving out of phase with each other. So a peak interacts with the trough and vice versa. And destructive wave interference, so they disappear. Now, this was actually an experiment done over 200 years ago by Young, a British scientist, and he did it with reflected light from a very thin window light source and a double slit. And what he found here were areas of very bright light, so what are called maxima. So maxima is the plural. And then areas of darkness, which are the minima. So what he observed on the screen was a band of white light, a gap, a band of white light, a band of white light. And actually the intensity dropped off the further away we went. So we had these maxima here, and that's where the light waves are arriving in phase with each other. So constructive wave interference, so a bright light, and then in between is where they're arriving out of phase with each other, and we have destructive wave interference. So that was one of the very first experiments to show that light had wave-like properties, which is good, and that's how we've thought about electromagnetic waves for some time. But and another experiment was done 100 years later called the gold leaf oscilloscope experiment. So let's think about what a gold leaf oscilloscope is first of all. So a gold leaf oscilloscope consists of a metal plate attached to a metal bar, and at the bottom of that metal bar there is a piece of gold leaf. And that part of the apparatus is in a box that has a window on it and a vacuum inside of it. So we're not expecting any the influence of air moisture or anything like that, or air pressure. So because this is a neutral, there's no overall charge on this. There is an equal number of positive and negative charges on this. And first of all, this plate is charged. And what that does is cause the gold leaf to deflect away from the metal bar here. And the reason it does that is because we've charged it, we've added extra negative charges. So the gold leaf is negatively charged, and the part of the post or metal bar in it is also negatively charged. So there is repulsion between them. And what the gold leaf oscilloscope experiment attempted to do was to release photoelectrons. So the idea was that we have our negatively charged oscilloscope, the gold leaf oscilloscope, and light was shone at the plate. And what should have happened at this stage, and did, is that electrons are removed from them. And they are called photoelectrons. They are electrons, but they're called photoelectrons because they have been effectively, this is a terrible word to use, but they've effectively been boiled off the metal by the light. Obviously, boiling isn't a process, it's just a way of thinking about it. So the light has caused electrons to be released, effectively ionizing the metal. So we are releasing electrons because they are absorbing the energy of the light. And different light sources were tried, but the two that we're going to think about is very bright red light, which was known to have a low frequency, and very dull blue light, which was known obviously to have blue light has a higher frequency. And the predictions from these experiments were that the bright red light, because it was very intense and had a very high wavelength, very high amplitude, so very bright, very intense, should have caused the release of photoelectrons. The very dull blue light shouldn't have caused the release of photoelectrons. We shouldn't have seen anything happen. The reason being, by the prediction, is that the very dull, not very bright blue light doesn't have much energy because it's got a low amplitude. So if we think about our two waves here, red light with a high amplitude, we would be thinking about having obviously a longer wavelength but a very high frequency. So that would represent the red light, and the blue light we would think about shorter frequency, but it's significantly smaller amplitude because it's dull, and therefore by predictions it wouldn't have as much energy. And what we would expect to see in the gold leaf electroscope is that once these electrons had been boiled off, so once these electrons had been removed, that the gold leaf should have gone back to its resting position because we removed some of the negative charges, so we were back to an equal number and positive and negative charges on here. However, that was not what happened. The bright red light did not cause the release of photoelectrons, but the dull blue light did cause the release of photoelectrons, and therefore the gold leaf went down. So this was the birth of the idea of light being able to exist as a particle. And from that, we ended up with an equation. And that was E equals HF. So E is the energy of the light, and it is equal to H, which is the Planck constant, multiplied by the frequency. So this states that the energy is proportional to the frequency, not to the intensity of the light. So we know that the frequency of the blue light is higher, and therefore the energy is higher. And in fact, the energy of the blue light is greater than the energy needed to ionize the metal and remove an electron. And we say that, in fact, the frequency of the blue light is greater than the F0, which is called the threshold frequency, which is required to remove an electron. And then obviously that the energy of the red light was less than the energy needed to ionize the metal and release a photoelectron. So this allowed us to start thinking about the idea of light being able to exist as both waves and particles. There were two behaviors of light: reflection and refraction, which can actually be explained both by wave and particle nature. However, this interference pattern is definitely described only by a wave nature. Also diffraction and also polarization. So these properties of light can only be explained by the wave nature of it. However, the photoelectric effect, which is what we've just been looking at, can only be explained by the particle nature of light. Now, the reason this is important is then 100 years after the work that Young did on looking at interference patterns in waves, the work was done on electrons. Now, electrons, lots of experiments had proved obviously that electrons can exist as particles. However, there were two experiments that were done. Davis and Germer in the 1920s was a diffraction experiment using nickel crystals. And then there was also a double slit experiment. And that double slit experiment produced exactly the same results as it did with light. So we ended up with a screen that showed that there was an interference pattern that showed that electrons could also exist as waves. So then from that was born the idea that wave-particle duality existed not only just for light, but also existed for electrons. And key one amongst that was the double slit experiment. So in that particular double slit experiment, we had a source of electrons, a double slit, and effectively we saw that same interference pattern. The details we would have to go through in a bit more detail, but we saw that same interference pattern of maxima and minima being produced by a beam of electrons going through a double slit.